Hi, welcome to my talk about the Mac in the Box project. This is joint work with Nemati. The project is based on an idea of Graham Steele and Mike Gordon, who both supported it in early stages back in 2013. Here's the outline of the talk. We designed the minimalistic token to secure password databases, the Mac in the Box. We use it as a case study to how we can conduct close-to-hardware verification in a traditional Ethereum prover, Hall 4, that is often used to verify hardware, but rarely used to make security arguments. We describe the desired security property for this device by simulation, similar to the popular universal composability framework. Besides password storage, the device can be used to harden protocols against host compromise, which we exemplify with the key exchange protocol and a protocol for second factor authentication. The purpose of the Mac in the Box is to secure password storage. The problem is well known. Hackers obtain access to an authentication server that holds the password databases. As users tend to reuse passwords for different services, the attacker gets now access to those too. It will take us time to get rid of passwords as an authentication mechanism altogether. Therefore, protecting against these attacks is a must. So how should we store passwords? Note that usernames are stored in the clear. Well, the first method is storing the password in the plain, like the usernames, but it is obviously insecure. The second method is to store the hash of the password, in which case the attacker has to brute force the password. Yes, but he can attack all users at once. A guess can be validated by comparing its hash to the hash of all users. We add a public random value to each entry, which is called the salt. Now, the attacker needs to compute a different hash for any guess and any entry. Still, even with salting, brute forcing is feasible, because modern computers can compute hashes very quickly. bcrypt is a way to purposefully slow down hash functions, so that instead of 100s of millions of passwords per second, the attacker can only compute thousands per second. This is the state of the art since the year 2000. Of course, these guarantees depend on the computation power of the adversary, and thus they degrade over time. Experts on password security propose the use of a high entropy parameter, which is hidden from the attacker, even if it manages to break in. For example, the main developer of John the Ripper, an infamous password cracking tool, proposes the use of the HMAC construction. It would look like this. The attacker obtains a password database whose entries are now protected with a key. The key is stored on a hardware token, such that the compromise of the authentication server does not provide information about that key beyond the ability to compute HMAC values. Password guesses have to be performed online and can be limited by the device. Password database breaches are very frequent. Here is just a list of a few of those. What's interesting to see is that all methods from the previous slide, including the most insecure ones, have indeed been in use. In 2011, PlayStation Network lost 77 million passwords in the clear. That's obviously bad. LinkedIn's 2012 leak demonstrated the perils of unsorted password use. Within just one day, most passwords were cracked. Despite bcrypt being recommended since the early 2000s, large companies still rely on sorted standard hashes, as in the case of Evernote. I will later come back to the Adobe leak, which featured the use of blockwise encryption, a very unusual choice in this case, which allowed for about 3 million passwords to be cracked in 3 days, without obtaining the key that was used to generate these ciphertexts. Ashley Madison's leak featured passwords that were stored as bcrypt hashes, which is good, but in parallel they were stored as MD5 hashes for the same entries, rendering the use of bcrypt moot. The latest leak I could find was from June. Still, a part of the database used only sorted SHA-1. To summarize, password databases leak shockingly often, and even high-profile companies have trouble securing them. Hardware tokens could provide an easy-to-use alternative. The downside is this method requires hardware support, obviously. hardware security modules are widely used in the public key infrastructure and in other security critical scenarios, so they are well known, but they are expensive. There are affordable alternatives, like the UBHSM and the S-Script Scrambler. They are implemented as USB tokens. They provide weaker performance, and they lack physical security measures like tamper-resistant enclosures, which traditional HSMs provide. But both these points are irrelevant in the current scenario. A downside for both kinds of HSMs is the lack of a white box audit. Specification level analysis for the UBHSM revealed severe flaws, but it can be configured securely. Independent analysis of the S-Script Scrambler pointed out that it is, I quote, "fine if you can guarantee the key will not be compromised." The problem is, you can't guarantee that. In this work, we design a minimalistic piece of hardware specifically to secure password databases and specifically to provide the trust that we can provide by verification. But defining what security is in this case is tricky. When we hash passwords, which properties do we want? The terminology and the algorithms that are used suggest that we want cryptographic hash functions. So we want a hashed password to be, well, a hash. But the guarantees that hashes provide seem insufficient. One wayness promises to protect the password as a whole, but it could reveal the first half of it. Collision resistance ensures that two different passwords do not result in the same hash, but this also does not really capture our requirements. When we think about the authentication property, MACs seem to be a much closer match. Unforgeability guarantees that without knowledge of the local parameter, the key is stored on the token, right? It is not possible to compute a MAC for a certain password guess. But a MAC could still reveal the password. As you can guess from the title of the talk, the output will include a MAC, but one that also provides confidentiality. So now that we think about confidentiality, we immediately think about encryption, right? Seeing that MACs do not necessarily hide the password, we can now at least understand Adobe's decision to stray from best practices and use encryptions. Of course, the mode of operation they used was a bad choice. Nevertheless, encryption, even if it's non-malleable and provides stronger integrity guarantees, is not really a good fit, as it requires the ciphertext to actually contain the plain text in the information theoretic sense, which is not needed in this application. None of these definitions match right away. But on an abstract level, we know what we want. Faking a password should be difficult, and the adversary should learn nothing more about an input than whether two inputs coincide. The adversary learns nothing more from the interaction than is best expressed via simulation. An adversary should not be able to distinguish between interacting with the Mac in the box on the left-hand side and a simulator that just reproduces a similar interaction by talking to a random oracle. A random oracle is a function that for each freshly received message M draws a random bit string of a fixed length. It records those pairs. So if the same M is queried, the same X is reproduced. It thus behaves exactly like a randomly chosen function. Even if the Mac in the box would morse some secret information about the key via the status register or have a similar side channel, this kind of definition would capture it. Okay, so here's the complete picture. The definition follows the real-world ideal-world paradigm. On the left, you see the real world. The environment interacts with the Mac in the box in two ways. As an honest user who issues high-level commands like compute a Mac or override the existing key. In fact, these are the only two commands. The protocol represents some system library that initializes the device, splits the message into blocks, supplies these blocks to the Mac in the box, and reads the results from the volatile memory. It communicates only a fixed number of bits per cycle. This high-level communication by an honest user is depicted in green. The low-level communication by the protocol or by the attacker in case of compromise is depicted in red. It consists of hardware-level input to the Mac in the box. This hardware-level input consists of 2 control bits, skip and move, a block length bit string, and a length parameter. We will go into detail about this in one of the next slides. The attacker can corrupt the host machine, which corresponds to a server breach, and then issue low-level commands. This describes the real world. In the ideal world, the honest user communicates with an ideal functionality that includes a random oracle. It is very simple to describe. When the user asks to set a key, this key is simply stored. When the user asks for a MAC with a certain message M, it concatenates this key K and M and queries the random oracle with this concatenation. It then returns the result. All the additional information that an attacker can obtain via compromising the server and issuing low-level commands can be simulated only by querying the random oracle via the ideal functionality. Part of the proof is to define a simulator such that no environment can distinguish these two words. As some of you might already see, this definition employs the well-known UC framework, Universal Composability Framework, where the environment represents honest users and the adversary at the same time. To make the guarantees more clear, from the construction of the ideal functionality, we gain, first, confidentiality. The output contains neither information about K nor the message M, as the output is merely the randomly chosen bit string by the random oracle. Second, unpredictability. The MAC computation yields unpredictable values for each K and M as long as K and M were not queried before, as the result is chosen freshly in this case. Determinism. If K and M were previously queried, the MAC will be the same. This is because the random oracle is deterministic and K concatenated with M constitutes the query completely. This guarantees that the MAC can be verified later. The fourth point, resistance against compromise. The 3 above guarantees hold even if the host system is compromised. So let's come to the Mac in the box. The Mac in the box computes a MAC based on SHA-3. This hash function is based on a sponge construction, which has the nice feature that it can be used to compute a MAC just by prepending the key to the message. This is why the device is called Mac in the box. In each cycle, the Mac in the box obtains 4 inputs, 2 control bits for whether the device skips this cycle or whether it moves from one state to another. We will see the 2 states that exist in the next slide. The other 2 inputs are bit string that gives the next block input, and the length parameter size that indicates how many bits of the block are supposed to be interpreted as the next input block. The other 2 inputs are block input, a bit string of block size, and a size parameter that indicates the size of this input block. The output consists of 1 bit to state whether the device is in the ready state. Again, we will see the states in the next slide, and digest for the output of the computation. Abstractly, the device can be in 2 states, ready and absorbing. In ready state, it should hold the MAC for readout. In the absorbing state, it computes this MAC. It should absorb the message block by block, but not provide any output in the meantime. The digest output is only updated in ready state. By setting the move bit, we can move between those states. If neither move nor skip are set, we interpret the block input buffer and the size as an input. We stay in absorbing mode as long as we receive inputs of full block length. That means that the size value equals the block length. Once we receive the first block that is shorter, We finalize the computation, update the digest register, and move back to ready. Pretty simple, isn't it? But the devil is in the detail, as always. And finalizing is not so easy. Due to the padding scheme that is employed and two extra bits, constants, that NIST added to distinguish SHA-3 from its variable length siblings shake 128 or shake 256, there are at least 4 bits that need to be added to each message. It's a padding scheme, so it might be even more than 4 bits. At least 4 bits are added to each message. That means if the message is short by 1, 2, or 3 bits, some of the padding or some part of these constants might end up in the almost full block, and some need to be added to the next block. So we need 3 additional states to remember how much padding we still have to apply. This part of the design was very difficult to get right, and several times the proof had to point us into the right direction. Finally, the key in volatile memory can be overwritten by providing it as input in the ready state. So let's come to the proof of security. Let me first clarify. We do not prove the security for SHA-3. Luckily, other people have done it. In fact, the inventors of SHA-3, Bertoni, Dame, and Peters and Asche, show indistinguishability from a random oracle. What we show is that the Mac in the box outputs exactly the information that the ideal functionality would output if SHA-3 was in place of the random oracle. From there on, ideal word security is just one heuristic step away. Let me explain what I mean by that. A good hash function has several security properties, but the most important one is that no attacker can distinguish it from a random oracle. But a hash function is deterministic, and a random oracle is a randomly drawn function. So how can this ever be true? The adversary can easily predict the SHA-3 hash for a certain value just by computing it themselves. With a high probability, the random oracle will provide a different hash, and it can be differentiated. The answer is that we never prove indifferentiability for SHA-3, but for the underlying construction, called sponge. This construction builds a hash and also a lot of other useful primitives from a compression function. In the SHA-3 standard, this compression function is deterministic. It is given, it is described. You can code it up. In the proof for the construction, it is a randomly chosen function. So this proof assumes that this function is randomly chosen, and then it deals with all the randomness that comes from it. It provides conditional results, because the more often the adversary can query the hash function, the more likely he can distinguish the two. Mathematically, we cannot conclude from this proof that SHA-3 is as good as a random oracle in applications. This is simply not the case. The use of the random oracle in place of a hash function is a heuristic. This has consequences for us when we want to form a security. A mathematically invalid step cannot be formally proven. Otherwise, our theorem prover would have a big problem. But somewhere in between the Mac in the box, which uses standardized SHA-3, and the definition, whose centerpiece is the random oracle, this step has to occur, unless we found a revolutionary way to deal with hash functions, but unfortunately we did not. So our strategy is to push this heuristic part as far to the end as possible and formalize all steps that are preceding it. Given that we cannot formalize the step anyway, and so far no one can, by pushing the step to the very end we can avoid probabilistic reasoning and simplify the theorem statement to talk only about input sequences rather than the adversary as a Turing machine. So we show the following statement. For all sequences of input that the adversary could possibly send, these two systems produce exactly the same output. This is a stronger property than computation indistinguishability that is usually used to compare words in the UC-like definitions. It gets rid of the environment and the adversary. Besides that difference, there's only one major difference to the security definition that we pictured earlier in the talk. The ideal functionality gives access to the actual hash function, as opposed to the random oracle. This proves that no matter how the attacker is trying to confuse the device, it is always returning digests that correspond to correctly padded hashes for the concatenation of key and message. The existence of the simulator, which we prove by defining it, shows that no information about the key is returned because the simulator never has access to it. Never is not quite correct. The simulator obtains hashes which depend on the key. But if we trust the heuristic and the indifferentiability proof for SHA-3, we obtain the confidentiality and integrity guarantees that the ideal functionality is meant to provide. We formalize the security definition, the Mac in the box, a simple UC-like framework, and this proof in Hall 4. Let's talk about applications. Such a small and cheap device can actually be very useful. The prime application, I talked about this, is secure password storage. As I already argued, businesses need to secure their password databases for the case where they get stolen. We use ProVerif's diff mode to formalize how the Mac in the box ought to be used in a password authentication setup and to show that it provides strong secrecy against offline password guesses in the symbolic model. As a toy example, we showed that two Mac in the box devices that hold an identical key can be used to establish a secure channel. This is done using a variant of the signed Diffie-Hellman key exchange protocol that uses MACs instead of signatures. The Mac in the box can be used to harden this protocol so that it provides perfect forward secrecy and post-compromise security, which roughly state that in case of server compromise, past sessions remain secure and future sessions can recover security. Using Temmer and Sepik, we verify these properties. Finally, a more realistic use case is having the Mac in the box be a second factor. We demonstrate that it can be used to authenticate users with the popular FIDO standard for universal second factor authentication. Again, we establish perfect forward security and post-compromise security for authentication using Temmer and Sepik. So let me now come to the conclusion. The Mac in the box is perhaps the simplest possible piece of cryptographic hardware that is useful. We invented it to provide the first full-fledged security argument for hardware design. The way we approached this proof allowed us to sidestep probabilistic reasoning and use traditional fear improvers. This has some advantages. These fear improvers have a small kernel and are thus very trustworthy. Perhaps more importantly, they are familiar to folks that verify hardware and they provide the libraries that they prefer. Finally, let me stress that this technique applies only in special cases where cryptographic abstractions are, by nature, heuristic. This includes the popular random oracle heuristic, but also for pseudo-random functions, which are means to abstract block ciphers. Thank you very much for your attention.